Hello, everyone. Today I'm going to discuss the topic of what is an adjuvant. The term adjuvant is often mentioned in vaccine and immunology research, but for many non-specialists, it's not as intuitive as the terms antibody and antigen. In fact, adjuvants play a key role in enhancing vaccine effectiveness. Today's presentation will help you understand the definition, mechanism of action, types, clinical applications, and future development of adjuvants. I hope that after listening, you'll gain a comprehensive understanding of the value of adjuvants in medicine and life sciences. Before we begin, let me outline today's content. We'll begin with an introduction and definition to understand what adjuvants are. We'll then review the history of adjuvants and introduce their mechanisms of action and major types. I'll then provide examples of their practical applications, including both commercially available adjuvants and their emerging applications beyond vaccines. We'll then discuss the advantages, challenges, and safety concerns of adjuvants. Finally, I'll look ahead to future developments in adjuvants and offer a summary. Why do we need adjuvants? The reason is actually very simple. Many antigens have limited immunogenicity. For example, after protein or peptide antigens enter the human body, they may trigger a weak immune response and fail to form a lasting immune memory. If such antigens are used directly to make vaccines, the protective effect is often not ideal. This is when adjuvants can play a role. Adjuvants can increase the sensitivity of the immune system to antigens, enhance the intensity of the response, and even change the type of immune response. For example, it can help induce cellular immunity, not just humoral immunity. In other words, adjuvants allow some originally not loud enough signals to be amplified into alarms that are enough to attract attention. The word adjuvant comes from the Latin adjuvare, meaning help. In immunology, the formal definition of an adjuvant is a substance that enhances the body's immune response to an antigen. Importantly, an adjuvant itself is typically not significantly immunogenic, meaning it does not induce an immune response on its own. It acts like a behind-the-scenes force, helping the antigen to be better recognized and remembered by the immune system. Think of it as a megaphone, where the antigen is the sound itself and the adjuvant is the tool that makes it louder and more widespread. The development of adjuvants has an interesting history. As early as the 1920s, scientists discovered that adding aluminum salts could significantly enhance the immune response of vaccines, leading to the classic aluminum adjuvant. It is still used in many basic vaccines today. In the 1990s, emulsion adjuvants such as MF59 were used in influenza vaccines, demonstrating that immune responses could be modulated through different formulations. In the 21st century, more complex combination adjuvants emerged, such as AS04, which combines monophosphoryllipid A with aluminum salts for HPV vaccines. Other examples include AS03 and Matrix M, which have played a significant role in COVID-19 vaccines. In recent years, adjuvants have also begun to move beyond the infectious disease field and into research on tumor immunotherapy, marking a new frontier. How do adjuvants work? There are several classic mechanisms. First, the depot effect. Some adjuvants can cause antigens to remain at the injection site longer, releasing them gradually, giving the immune system more time to recognize them. Second, they activate innate immunity. Adjuvants can stimulate the body's innate immune receptors, such as TLRs, toll-like receptors, triggering inflammatory signals. Third, they enhance antigen presentation. Adjuvants make antigens more readily taken up by dendritic cells and macrophages, allowing them to be effectively presented to T cells. Fourth, adjuvants can also promote cytokine secretion, attracting more immune cells to participate in the response. Thus, adjuvants act like a switch, not only amplifying the signal but also guiding the immune system's response in the right direction. There are many types of adjuvants, which can be roughly divided into several major categories. The earliest mineral salts, such as aluminum salts. Emulsions, such as MF59 and AS03. Adjuvants targeting immune receptors, such as CpG oligonucleotides and MPLA. Plant-derived saponins, such as QS21 and Matrix M. And emerging adjuvants based on nanoparticles and liposomes, which can be delivered with antigens to improve stability and efficacy. Each type of adjuvant has its own advantages and disadvantages. For example, aluminum salts are safer, but tend to favor humoral immunity, while TLR agonists can more strongly induce cellular immunity. The importance of adjuvants can be more intuitively understood by examining approved vaccines. Aluminum adjuvants have been used for nearly a century and are found in hepatitis B and diphtheria tetanus pertussis vaccines. MF59 is used in influenza vaccines to enhance protection in the elderly. AS04, a combination of aluminum salts and MPLA, is used in the HPV vaccine Cervarix. Matrix M, used in the COVID-19 vaccine, enhances its immunogenicity. It can be said that adjuvants have contributed to the success of many vaccines. The applications of adjuvants are not limited to traditional vaccines. In veterinary vaccines, adjuvants can help livestock and pets develop better immune protection and reduce the risk of infectious diseases. In cancer immunotherapy, adjuvants can activate the body's immune system, helping it recognize and kill tumor cells. In allergy treatment, adjuvants can help modulate immune responses and reduce the intensity of allergic reactions. Even in the field of drug delivery, researchers are exploring the use of adjuvants in combination with nanoparticles to achieve the dual effects of targeted delivery and immune enhancement. So, what are the benefits of using adjuvants? First, they can significantly enhance the immune response, preventing vaccine inefficacy. Second, they can prolong immune protection, reducing the need for frequent booster shots. Third, they can facilitate dose sparing, meaning that the same or even better protective effect can be achieved with a reduced amount of antigen, which is extremely valuable in large-scale vaccination. Fourth, different adjuvants can also help adjust the immune response type, such as favoring cellular or humoral immunity, making the immune response more targeted. Of course, adjuvants aren't perfect. They can cause side effects, such as redness, swelling, and pain at the injection site, or even systemic reactions like fever and fatigue. From a regulatory perspective, adjuvant approval is more rigorous because their mechanisms of action are often complex. Developers must strike a balance between enhancing immune efficacy and maintaining safety. This is why, despite the importance of developing new adjuvants, few have actually made it into clinical use. Looking ahead, adjuvant development will focus on several key areas. First, adjuvants based on nanotechnology and novel biomaterials will facilitate more precise immune regulation. Second, personalized design will allow for the selection of the most appropriate adjuvant combination for different populations or diseases. Third, combination adjuvants will leverage the synergistic effects of different mechanisms. Fourth, adjuvants will be crucial in responding to future infectious disease pandemics, helping to rapidly enhance the immune response of vaccines and improve population protection. To summarize, adjuvants are essentially immune enhancers. They aren't antigens themselves, but they enhance the effects of antigens. They are indispensable in vaccine development and are also expanding into areas such as cancer immunotherapy and novel drug delivery. Going forward, we must fully leverage the immunological advantages offered by adjuvants while also carefully considering their potential side effects and safety. In short, adjuvants play a low-key, yet crucial role in modern medicine. Thank you.